Okay, welcome to lecture number 3. So, what we are going to do is we will start with where we finished off in lecture number 2. So, let us recall what we did at the end of lecture number 2 was we had said that if you know that you have n electrons per unit volume, which is this n right here, if you have n electrons per unit volume, then if you start filling in, now you have different k states. We have derived quantized k states available, and now we said that if you want to take these n electrons and start putting them from lowest energy up, slowly start putting them up. We will start looking at this graphically also a little bit. As you start putting them up, then you will fill up the last electron up to the energy level EF, which is this energy, and this relationship between them, this n and this EF, was derived as to be this right here as shown here. Similarly, we had said if you want momentum, that if you want to do momentum, then this momentum was equal to HKF, and even this you can now is in terms of, so this quantity n, in terms of n you can also determine momentum. Once you can determine momentum, then in terms of this n you can also determine what is the Fermi velocity. And when we say momentum, we mean momentum of the electrons which are at the Fermi energy. That means the highest energy which electrons are having. From lowest energy onwards, this is up to that energy where electrons are filling up, and the velocity of those electrons then is also given by this quantity, which is where we finished in the previous lecture. Now, let us look at this a little bit further. That we also said that now that you know, since you know already how to calculate this quantity n, so substitute n into this equation of Vf, and we said Vf you will find is about 10 to power 8 centimeters per second. That is the kind of velocity which you have, which means that you are in about 1% of velocity of light. Remember, in Drude's theory, this velocity turned out, the velocity of the electrons that were conducting turned out to be 10 to power 7 centimeters per second. So, that is the difference we have gained in free electron. That is what the free electron theory is saying so far. Now, we will move forward in this lecture 3. What we will do is that we will look at 4 topics today. We will look at the density of electron states. This is a side topic. This topic is going to be useful when we start doing semiconductors. Then I am going to use the results from this. Also, after that we will start looking at electrical conductivity, which we derived in context of Drude's theory. Now, we will start looking at that from the point of free electron version. Once we have done that, I will show you the difference between Drude theory and free electron theory. Finally, today I will show you that even free electron theory has serious limitations, and we have to see what next. Okay, so that is what our this lecture number 3 would be today. Okay, so let us get going. Let us start with this density of electron states. Let us start with this topic. So, what we had derived was that let us turn around this equation for Fermi energy. We had derived, if we take this equation right here, if we take this equation and turn this around, then I would write this equation, then I would write it as n as equal to, I will write n as equal to 1 by 3 pi square 2 me divided by h bar square power 3 by 2 E f to power 3 by 2. Okay. So, what do we mean by density of states? Let us first define it. Meaning of density of states. This is a symbol I am going to use. So, we can say that G of E dE is the number of electron states in energy interval of E and E plus dE. So, this is the number of electrons, that is number of electron states which are in energy E and E plus dE. So, that is what the meaning of this density of states is. Now, I would like to pause for a minute and clear up one idea which may become confusing later. So, let us clear it up right now. First, let's first thing is we could also define something called as density of k states. Remember, what we have is, the way you should think is like this, that there are allowed k energies, there are allowed k states, not k energies, they are allowed k states. So, if you have different k states which are allowed, then you can ask the question, what is the density of these k states? So, therefore, I could have defined another quantity called density of k states. Then, since each of these k states can take 2 electrons, so if I multiply by 2 these density of k states, then I would get what we call as density of electron states. So, either you work with density of electron states, or you can work with density of k states. As long as you remember whether you have multiplied with this factor of 2, then you are okay. In this course, what we will do is, we will never deal with density of k states, we will always deal with density of electron states, which means that there is difference of factor 2 only. That means I have certain density of k states. Since each k state could have taken 2 electrons, spin up and spin down electrons, therefore, I will always call that density multiplied by 2 as the density of electron states. Remember, these are density of electron states. It does not mean that electron indeed is necessarily present on those states. Is that the states are there, then that means electron can occupy that. It is not necessary that electron does occupy those states. So, if in fact, if you want to know whether electron is there or not, we will have to do something else, which I will do later. But notice, I have been silent so far about this aspect, and I have derived these relationships right here, saying that if I have n electrons, up to what energy they will fill. In that sense, it is a hypothetical question, that if I have an electron, then how far they will fill. That is the question. That is the question I have answered. I have not said whether I have indeed put those electrons in or not. So, you can think of it like that, or you can think differently, that indeed all these states are indeed filled with the electrons. You remember that all these calculations are really valid for 0 k. It is possible, which we will see later, that if we go for higher temperature above 0 k, then some of these electrons could go to even higher energies, leaving some of the states vacant. In that case, these formulas directly will not be valid. So, that is why I am saying that you think as if I have all these k states, and therefore electron states multiplied by 2, that is, and if I had n electrons, then how far they will fill is the questions we have answered so far. And indeed, if they do occupy, if that means probability of occupying those states is 1, that means indeed all those states are occupied, then precisely these would be the energies, these would be the momentum, and these would be the velocities, the Fermi velocities, etc. of those electrons. Okay. So, with this background, now it is very simple to derive remember, now I can, instead of writing this Fermi energy, let me write another quantity called n prime, and I will write the same expression as like this. This n prime I am using only for explanation. In future, I will drop this and keep calling back again n itself, so that there is no confusion. Sorry, let me remove this f here. I just want E. What I am trying to show is, by exactly same logic, instead of saying, earlier I said I have n electrons, if I have n electrons, how far they will fill, and I defined that as the Fermi energy. But you could think slightly differently. The way we could also think is that up to energy E, I can fill total of n prime electrons. And if I go slightly dE energy higher, then I would have filled this n prime plus dn prime electrons extra, and we are seeking what is that number of electrons. So, if we can calculate that number of electrons, then we can immediately define our GE. Clearly then, this quantity GE would be equal to simply dn prime by dE. Why? Because dn prime would be equal to GE dE, and this is the quantity we are trying to. What does that mean? This is the number of electrons in energy, this is the number of electrons, read the definition here, this is the number of electrons states in energy of this interval. So, as I explained, n prime electrons are filling up to energy E, and if I go slightly higher in energy dE, then the number increase in electrons is dn prime. So, we are basically trying to calculate dn prime by dE for the density of states. So, now once we have this definition, it is straightforward enough to write this density of states as being equal to just taking the derivative of this quantity n, dn dE, call it prime or do not drop this prime, does not matter really, 1 over 2 pi square to me. I presume you can carry out this derivation, I have just written it out here, and to save time I am just writing it down, 3 by 2 energy to power now half. That is what density of state is. So, density of state goes as square root of energy. So, if this is energy, then G of E goes as square root. It goes something like this. Okay. All right. Given this, now we stop at this topic, this density of density of electron states. Just remember this expression. I am going to use that about 5-6 lectures down the line. I will start using this when I start doing semiconductors. But in context of free electron theory, we have derived this, we have given this definition, and from given this definition which we will use subsequently. So, now let us move on to the next topic, which is electrical conductivity. The free electron version is now what we want to do. Okay. So, what do we have? We know that h bar k is momentum. So, if I divide this by mass of electron, I get velocity of any electron. I get velocity of any electron in this way. Now, let us look at this. The way I am saying is that if you have all these k states, let us say kx, ky, kz, and in this, and there is a sphere up to which electrons are all filling up. All these electrons are filling up to this kf, and this is what kf is. So, up to here all these electrons are filling up. Now, you notice that for every k in Fermi sphere, there is a minus k vector. There is a minus k vector also. What does that mean? For every velocity of electron, there is a exactly opposite velocity of electron also. So, net velocity is equal to 0. So, that means clearly if nothing, then this electron cannot, material is just as is, there is no conductivity. We expected there should be no net velocity. If there was a net velocity of electrons, then we would have current. But clearly without application of electric field, we can't be having current, and therefore, as we expected, the net velocity must be 0. But what happens if I apply an electric field? If we now apply electric field, then what happens? We know that dP, this rate of change of momentum, now should be equal to minus q times E, the electric field, which is a minus sign because the electron, and q is the absolute charge, positive number 1.6 into 10 to the power minus 19. So, that is that number. Okay. Anyway, so this is the rate of change of momentum, which this implies I can write this as h dk dt as equal to minus q times this electric field E. So, what does this mean? So, in time t, this Fermi sphere starts moving. This starts moving. How does it move? That if I integrate this expression right here, what do I get? I get that k vector at any time t then will be equal to k vector at time equal to 0. That at time equal to 0 is when we apply the electric field. So, at t equal to 0 electric field is applied. In time this k vector begins to move and this becomes equal to q minus q E by h bar t. This is the amount by which this k vector moves in time t. Now, we face with same problem, that in time, as time increases, this k vector can keep increasing. It is like shifting of origin of the Fermi sphere. We can think of this as follows. We can well, I will draw in a minute, but before that you can think this is just the center of the Fermi sphere changing from a different k position, moving from one k position to another k position. But the problem is now that as t is changing, this Fermi sphere keeps shifting. Now, this causes us problem, same problem which we had when we started, that if I apply electric field, if there is nothing to damp the motion, then the current will continuously increase for a given electric field, which is contrary to our observation. Same thing will happen here. If k continuously increases, then therefore, the same token this V will continuously increase and therefore, current will continuously increase. Current will also continuously increase. So, we face with exactly same problem as we started in the lecture number 1, which is where we started Drude's theory and we invoked collisions, which was really giving us damping, and hence the velocity we found to be a average velocity was a fixed velocity when we included collisions. Now, in this free electron theory, we will make no such statement as to what the mechanism of this damping is, but we know that from experience there must be some damping. So, let us assume, let us invoke the same time t tau. Let us say that by some mechanism there is a relaxation time called tau. The same relaxation tau we started using in Drude's theory, maybe because of collision with ions, but same idea that in time tau, that this k state changes to that value, to k state changes up to this time tau, and then it is held at that. For me, then no more changes happen. You think of tau as the relaxation time, mean, if you want to think same way as Drude, then mean time between collisions, and therefore, after time tau, on average the value of k, average value of k would have then in that case become, I will write then the same expression by saying k then will become at, after applying electric field, k then will become equal to k whatever it was at 0 minus, or plus I should say, minus q times, let us see what the expression was, minus q E by h bar, minus q E by h bar tau here now. So, if tau is the relaxation time, then k average value of k state where it is applying when you apply electric field is then k of tau, this quantity. So, effectively therefore, I can show in 2 dimensions, it is easy to show. You can imagine this to be 3, you can imagine this as a 3-dimensional figure also. What I will do is, what I will show you is, let us say this is kx, let us say this is ky, right, and let us say that I am going to draw it as a circle, or everything, not a sphere, but a circle in 2 dimension. You can keep imagining this as a 3-dimensional figure as a sphere. So, what I will do is, I will draw a circle here, let us choose a different color. So, we will choose a circle here like this. So, here is a circle I have drawn here, and this is at t, this is at t equal to 0, t equal to 0, and what we have done is, we have applied an electric field E, let us say we have applied an electric field in x direction. Initially at t equal to 0, we have electric field equal to 0, and then at t equal to 0 turn on an electric field. And what happens? Then when we apply electric field, what happens is, another picture we will draw here, right here. This is kx, this is ky, and let me draw the same sphere first, the same sphere which I had, but I will show it as a dotted line now. So, this is the sphere at t equal to 0, which originally I had drawn in the previous figure also. Now, I will show with another color pen, let us say blue. Let us say now I have a situation where this is T is equal to tau and E field which I have applied is, let us say, minus E magnitude in x hat direction. We applied this field, let us say. If we applied this field, then this, now see where the k will be. Every k point, whatever the k point was at time equal to 0, in time tau, its value would be that number plus this number, and so I have taken E to be minus field. So, there will be a plus number here. So, it is going to shift in the x direction. So, let us draw that sphere also, that circle now in this case, and you can imagine sphere. Then this, after shifting, will become something like this. So, this whole thing has shifted, its center is shifted to here. Now, this whole thing moves something like this now, something like this. So, this was at t equal to 0 and this is at t equal to tau. So, what do you notice? So, what do we see here? So, what has happened? My figures are not so nice. You can imagine all of these to be circles, but anyway. So, now what do you see? Now, notice that whereas in this particular case, for every vector k, I had exactly equal minus k vector also, and therefore, what happened was, for every vector k, any vector k, I had a equal and opposite minus vector also. Therefore, net velocity was 0. When E field was 0, at that time the net velocity of electrons was 0 and therefore no current. But now you notice in this blue circle, which is what it will be at t equal to tau when I have applied electric field. When I applied electric field, now the net velocities will not cancel. Now, notice again a velocity like this will have exactly a component like this, and all these velocities will cancel out. But the electrons which have velocities corresponding to k states which are near the surface of this blue circle, those velocities now will not cancel out. What does that mean? This is very important fact. This is very important. Therefore, since now electrons, the electron velocity near Fermi surface will not cancel out, meaning net velocity of electrons will be due to those electrons which are near Fermi surface. What does that mean? Let me repeat what I said again. I said that most of these velocity, like here this k component will cancel out with this minus k component, but the k, now there will be those k's which will not cancel out, and on those k's will be the ones which lie on the surface, which are not going to cancel out anymore. So, what do we see? That the electrons that conduct implies the electrons that conduct are ones near the Fermi surface and have velocities approximately as Vf, Fermi velocity, which you recall was 10 to power 8 centimeters per second, not 10 to power 7 centimeters per second as we assumed in Drude's theory. Therefore, you can see the first error which was in Drude's theory, and now we have a better estimate of what the velocity of electrons that conduct should be. Now, I will not derive the expression, but only thing is that if you go through a process of calculating this average net velocity through this process, exactly the way it has been described, if you carry out summation of if you average over all the velocities and calculate what the next net velocity is, and you also calculate what will be the number of electrons that will be what is the number of those electrons which will be therefore conducting, then you will find, if you go through this whole process, what I will do is I will write the final expression, that in this case we find that the conductivity will becomes equal to 1 by 3 q square, the same tau which is going has to appear, and this becomes equal to then tau. I am going to reduce the quantity as g itself. This is the density of electrons near the Fermi energy. So, this expression for conductivity becomes this, which should make sense. It should have a dependence on the number of electrons that are near the Fermi energy, and it should depend on the velocity of the electrons, which is velocity of those electrons which conduct, which is the Fermi velocity. So, this gives us a estimate of what the conductivity of a material will be. Anyway, this was only side topic. I just, since we derived the same expression for Drude's theory, so therefore, I have done that for free electron theory. Now, there is a time to take stock of what has happened. Let us analyze what we have gained so far and where the problem continue to be. So, let us first start looking at what have we gained. Drude's velocity versus, so I will talk about Drude's, not velocity, Drude's theory versus free electron theory. Let us do this first. What has happened? What have we gained by doing this free electron theory? Clearly, now in this case, our estimate of things will become better wherever velocities were involved. Wherever the velocities were involved, since we know that the velocity of order now between Drude's theory and free electron theory, we found a discrepancy of order of magnitude in velocity is being higher in case of free electron theory. Then we know that Drude's theory, wherever velocity of electron will be involved independently, so that it does not cancel with something else, then in that case free electron theory will make a better prediction than Drude's theory. In order to really show you advantage of free electron theory, I will take you through some of the topics, a couple of topics which may sound out of context in the context of the electronic properties of material. What I am going to talk about is thermal conductivity and thermoelectric power, to just show you how free electron theory gives you better estimate than Drude's theory. So, let us just look at two topics in this case. One is thermal conductivity . In metals. In particular, I am going to talk about this, what is called as Weidman France law. Let me try to show you what have we gained. Okay. Now, if we, without any, remember, the conduction, thermal conduction in metals occurs by same process by which electrical conduction occurs. That means, the mechanism by which the heat transport, so remember we said electron arrive at local thermal equilibrium. So, now if electrons are moving around due to electric field, for example, if you wish, then that gives you current, but then this motion of electrons also carries heat. So, the thermal conduction in metal also happens through this exact same motion of electrons. So, in that sense, we are not talking out of context. When we talk of thermal conductivity in metals, we are at microscopic level, at atomic level, we are talking about the same process which we talk for electrical conduction. So, if you therefore, we are free to apply the same theory to develop the idea of thermal conduction also, in which case by in Drude's approach or classical approach, without proof, I will write this thermal conductivity, a capital K, to be equal to 1 by velocity square tau times Cv. In context of Drude's theory, if it is derived, then this quantity is half, derived as half V square tau times specific heat Cv. This is the specific heat, of a material, and this also can be written as 1 by 3 V L, L being the L being V times tau, of course being that L, so 1 by 3 it should be here, 1 by 3 V L C V. So, either way, remember V times tau as being equal to the L, that is what we are using here. This quantity is derived like this. Second thing, also I will say that by classical approach, by same approach, specific heat is derived as 3 by 2 n times Boltzmann constant Kb, that is the Boltzmann constant, and estimate of velocity is by half m me v square is equal to 3 by 2 Kb times T, which you have seen before, which is same thing. This we have used before also in when we are doing Roots theory. I am giving you two expressions right here. This I am giving you without proof, that in root context of Roots theory you can derive specific heat of metals to be 3 by 2 n K times K Boltzmann constant, and you can derive the thermal conductivity by same transport mechanism to be equal to 1 by 3 V square tau Cv, or 1 by 3 V times L times Cv. So, this you can derive by classical theories, Roots theory. Now, there is a law which is called Weidman France Law, which says that for metal K divided by sigma T will be a constant, and this is this law. So, this is what this Weidman France law is. Let us derive this expression for it now. So, what will this quantity be equal to? So, this we are going to derive as, so let us write down, so this quantity, this K sigma by T will be equal to, let us substitute K 1 by 3 V square tau Cv divided by conductivity. Remember what is conductivity? Conductivity we had derived as equal to n q square tau by me, that is what we had derived this as. Therefore, we can write, substitute that in here. So, n q square tau by me times T, that is what we are going to substitute here. Also, for now we are going to substitute, make two substitutions, which is what we are going to substitute is, first we will substitute for velocity, this square of velocity, which we will estimate from right from here. So, we will say V square as being equal to 3 Kb T by me, that is what we will substitute in here, and we will also substitute Cv. Cv was equal to, of course, we have written there, Cv is already there given here. So, let us substitute this in here also. So, 1 by 3 we are going to write, and then for V square we are going to write 3 Kb T by me, and there is a tau here, and then Cv we substitute in here as 3 by 2 n Kb, and this whole thing divided by n q square tau me by T. Now, notice this tau and tau cancels, this T and this T cancels, this me and me cancels, and this n and this n cancels. So, what are we left with? And let us allow this 3 to cancel with this 3. So, what are we left with? We are left with essentially 3 by 2 Kb by Q whole squared. Indeed, it is a constant, Boltzmann constant divided by base principal charge, electronic charge 1.6 into 10 to the power minus 19. Indeed, this is constant, which is what is observed in this Weidman France law, which is a experimental observation. even in Drude's theory, this value came out as a constant, which, and this value when plugged in, you can plug in this value, what you get is a number which is like 1.11 into 10 to power minus 8 watts ohms per Kelvin square. Now, if you look at this number is about only half of what actually is observed. So, it is pretty remarkable that even Drude's theory basically predicted right result. Everybody thought that this Drude's theory is predicting this Weidman France law very well, because only half of what is experimentally observed. The thing of it is this, that what happened was that electronic contribution, the electronic contribution to specific heat is at least 100 times more than observed. And what is the electronic contribution? Remember, 3 by 2 n kb. This is the classical theory, and this is the contribution to specific heat, and this number is at least 100 times more than ever know any than what the electronic contribution to specific heat is. So, what happened? How did it still work? Now, let us go back. If you go back, notice there is also a v square term in here. There is a v square term also in here, and this v square is what has helped. This, and remember, in Drude's theory, we also underestimate velocity by 10 times. So, this underestimate of velocity 10 times, and we have a v square, and overestimate of CV 100 times. Therefore, two errors cancelled out, and you got something very close to what reality is in Drude's theory. Times. Let me just repeat this part. Okay, so this is in the Drude's theory. This is in the Drude's theory. Now, let us see what happens in free electron theory. In free electron theory, the estimate of CV becomes equal to pi square, without proof again. I will just simply give you by free electron theory what happens. Kb Boltzmann constant, this is Fermi energy now, n times kb, as opposed to in Drude's theory, where it was CV equal to 3 by 2 n kb. This factor right here, this factor which is right here, n kb, remember, is same in both of them, classical theory, the free electron theory. This factor, if you look at even at room temperature, this T at room temperature, if you look at this factor, this pi square by 2 kBT by EF, this factor is at least 100 times smaller than this 3 by 2. Compared to 3 by 2, this factor is about 100 times smaller, which is why I was saying that electronic contribution to specific heat is at least 100 times more than observed, and this is what electronic contribution really is, which is being predicted well by this free electron theory. Now, if you put this simultaneously, estimate its velocity, if you estimate by the velocity by 2 times EF by ME naught, that is according to half mv square mev square mass of electron as equal to the Fermi energy. If you equate that to Fermi energy, then you estimate the velocity to be like this. If you estimate the velocity to be like this, then remember, in classical theory we had estimated this by as equal to 3 by 2 kb t, and we had underestimated this velocity 10 times. So, now this velocity estimate is 10 to the power 8. centimeter per second as we have derived in free electron theory earlier. If you now plug in these numbers, then in this case K by sigma T becomes equal to pi square by 3 Kb by Q whole squared. Now again a constant number, even by free electron theory we are getting K by sigma T, the Weidman France law which says that it is a constant. Indeed, we find by free electron theory also that K divided by sigma T is a constant, and now if you substitute in the numbers, this number comes out as 2.44 into 10 to the power minus 8 watts ohms per Kelvin square, which is a even better estimate of, which is now the correct estimate of what we also observed value, because remember I said this was 1.11 in case of roots theory and it was about half of what is actually observed. Now this is now beginning to predict even better. Of course, it is a minor gain. Now if you look at another example, which is a thermoelectric power, now you will see what we are going to do is, in case of thermal conductivity, thermal conductivity, the two errors, velocity and specific heat, cancelled out each other. Now we are going to take an example where there is no velocity term, but only CV term, which means now Roots theory will completely go haywire, and I will show it to you that free electron theory continues to predict, now predicts much better, and that is in case of thermoelectric power. Let us look at this, which means if I take a hot bar, if I take a bar of a material, then remember what will happen if I keep one end at T1 temperature, other one at T2 temperature, where T1 is greater than T2, then what will happen? Remember, electrons come to thermal equilibrium, we had assumed that, a local thermal equilibrium. So the ones which are near T1 will have higher energy, higher kinetic energy than the ones which have are at other end, at T2 end, which have lower kinetic energy. So there will be net flux of electrons going from T1 side to T2 side, but that cannot continue indefinitely, because there can't be a current flow in this system. So what will happen, as more and more electrons move from T1 side to T2 side, temperature side, then electric field will set up. This electric field will oppose the motion of electrons from T1 side to T2. That means due to electric field you will have electrons going from T2 to T1, and due to thermal energy the net flow will be from T1 to T2, and in equilibrium these two will balance out, so that there is no current. And this is well known effect called Seebeck effect. Remember that if you, the electric field that will develop if you apply a temperature gradient across a bar, then the field that will develop inside, so that the system comes in a steady state, is E equal to Q times gradient in temperature. That is the electric field that develops, and this is called the thermoelectric power. And this is well known Seebeck effect, which you have seen in various situations, you taught in schools also. So this is the thermoelectric power. Now if you go through this again to have net zero velocity, so there is no current flow. When there is a temperature gradient, electric field is also developing and both balancing, so there is no net velocity. Under those conditions, the expression which is derived for Q is that Q should be equal to minus Cv divided by 3 NQ. That is what this Q should be, thermopower. Now notice, in thermopower we only have Cv. If we incorrectly estimate it, we are going to get a wrong thermopower, and if we put it right number, then only we get thermopower, which is okay. If we use classical estimate of specific heat, so Roots theory, classical estimate, if you use estimate, we get Q which is equal to minus 4.3 into 10 to the power minus 4 volts per Kelvin, which is 100 times more than observed value. Clearly then since estimate from free electron theory of CV is 100 times less, we will start getting right numbers. So that's really the success of free electron theory. So this is where the free electron theory has, there's an improvement from Drude's theory, from classical theory going to quantum mechanical free electron theory. This is where we start seeing improvement. Now let's look at also failures of free electron theory. And there are many. Now notice, what about Hall coefficient? Recall RH was equal to 1 by NQ. Now notice that Drude's theory we found that it does not work for metals such as aluminum. Now when you did free electron theory, what have we gained? Nothing. We cannot say anything about Hall coefficient. I mean, no improvement. There is nothing, only N appearing here. That estimate hasn't changed, and therefore we can't. And we found for aluminum the Hall sign of Hall coefficient was positive. The Hall coefficient was the Hall coefficient. Yeah, it appeared as if holes were conducting. So therefore, in free electron theory also we make no improvement in this regard. Same problem in magnetoresistance. In this regard also, the field dependence of magnetoresistance is again not predicted. We have nothing in this theory which says that. Let me ask many questions to you now as we start discussing this. There are too many things which are a problem. How would you explain that carbon? Carbon comes in many forms. Diamond, it comes in as graphite. Why is it carbon which is insulator? Why is graphite which is conductor? Why does that happen? So this France Weidman law, it is obeyed well up to room temperature, but if you go to lower temperatures, then even France Weidman law is not predicted well by this what is observed. There is discrepancy between free electron theory and what is predicted by what is observed. Similarly, the dielectric constant of a material could be very complex, which is not appropriately predicted by free electron theory. Now, I already talked to you about, and I give you already a hint that when you talk about when you talk about conductivity in graphite or and diamond, now both are carbon. There is nothing we have said about differences between graphite and diamond, and therefore the difference in conductivity. We just can't bring it in. Why is aluminum good conductor, but bismuth and antimony, which are also metal, which are not? Why boron is insulator? Why boron is insulator? Now these are the things which are not coming, which are our observations. However, this free electron theory, we are not gaining anything out of it. Why is it so? You should already have a clue that our materials have crystal structure. Their materials they have a structure also. They are underlying atoms. There is periodicity in them. What does that mean? Remember, the clue comes from graphite is conductor, diamond is not. What is the difference between them? Both are carbon based materials. Now all we have done is, in copper we have taken copper atom and considered valence electrons and went ahead and did both these theories. But you see, there is an underlying lattice, underlying periodicity in these materials. This periodicity, an electron wave which is coming. Now you notice this electron wave is travelling. Now there is an interference of this electron wave. If the lattice is perfect, then there could be constructive interference and this electron wave could just simply go through. Whereas if you break the periodicity of the lattice somewhere, then you can have destructive interference, and therefore you could have the electron wave dying out, and that means conductivity being low. Now all this, therefore in order to explain conductivity, we must take into account what is the underlying structure of the material. So what in the next lecture I will do is, I will cover two topics. One, just to build up the case, I will cover two topics. One is that we will start with crystal structure of material, Then after that I will take you through something what is called reciprocal lattice. Some of you would already be familiar with it in context of X-ray diffraction or electron diffraction. So you see, we will go through those two topics first, and then you will see the relevance where we are heading. What ultimately I want to do is, now I am going to write down here that what have we done so far. We have said that energy is equal to h square by 2m k square. What ultimately I want to show you is that there is something called Ek diagram. So, I plot this Ek, k versus energy, then clearly it looks something like this. It clearly looks something like this. This is this expression being plotted here. What am I doing? Of course, k appears only at discrete levels. Allowed values of k are only these. These are the allowed values of k, and corresponding energy is plotted here. But now these k are so closely packed that we draw them as continuous line. That black line I have drawn is sufficient enough, because these k are so close. In this picture I have shown you by red dots which are far apart, but in practice they are so close that there is no need to show those dots. They look like the black line, which is a continuous line. Now what happens? What we have done so far is that when we start filling up electrons, we start putting them 2 electrons on each of these k states. In each of these k states we start putting 2 electrons, and when you start putting them in, we fill up to, let us say, this energy, and this energy we call as EF. This energy we call as EF. That is the something which we have done. I have shown you. The question is, what is this quantity? You also remember I have pointed out that this is a Ek diagram, meaning this energy versus momentum diagram. K precisely represents momentum as well. H bar multiplied by k represents momentum. So, if I get a proper Ek diagram for each material, then I should energy and momentum. Those two quantities are sufficient to do all the dynamics we want to do. Whatever you want to do with the dynamics of electron, you can do if you have a Ek diagram. So, essentially for real materials, I want to do this Ek diagrams. And in order to understand this Ek diagram, I must understand k. This k, remember, in order to plot like this, I have drawn it as a scalar, but the k really is a vector. K is a vector, which is in which direction should I draw it? How to draw this Ek diagram? This issue we will start looking at almost 2-3 lectures down the line. Slowly we will build the case. In order to do so, we have to understand reciprocal lattice, because k belongs to the reciprocal space, and in order to understand reciprocal lattice, we must do real lattice, which we will start next lecture. Thank you.